Okay, so the p-value, which we talked about, the definition is on the alpha lesson for 9.1. You are accountable for this definition. The p-value is the probability of getting a test statistic, which means a z-score or a t-score, as or more extreme than what you got by chance alone. Meaning, by chance alone means sampling variability, given the null or true. Okay? So if the p-value is small, if it's less than the alpha level, you reject the null. If the p-value is large, the probability of this happened by chance alone is greater than the alpha level, we fail to reject the null. Okay, and people get confused about this, when to reject and when to fail to reject when they compare the value to the p-value. You have to work this out. I mean, I can see getting confused when you first start doing it, but by the time we get to and move in chapter 9, this is not complicated. You compare the p-value to the alpha level. If it's small, that means you're in the tail. If you're in the tail of the curve, you're rejecting the null. The null is in the center. If the p-value is greater than the alpha level, then you're closer to the center. You're closer to the null, so you fail to reject the null. Okay? So we told you this, that the United States Supreme Court is on board with 5% as an alpha level. Okay? But if it's something that, like if it's a medical procedure, we want to have a stronger threshold. You would generally use something smaller than 5%, 1%. Sometimes you would use something not as small as 5%. You could use 10. But ready? If you don't know, use 5%. That's the default. You need to come up with the p-value before you collect your data. If you say it's unethical, right? If you say my p-value is my alpha level is 5%. I have to determine the alpha level first. My alpha level is 5%, and I get a p-value like less than 1%, right? You're in the tail. You're rejecting the null. You can't change the rule and say, well, I'm going to change my alpha level to 1%. That makes it look like, it was harder to get this. No. You pick the alpha level first, and then you compare it to the p-value. Okay? So here's an example. We'll give you a minute to read this. Okay, so what's happening here? They're saying the null is 30 hours. And they're testing the alternate that it's larger than 30. Well, really the whole screen is about the last two lines. The p-value is 7.17%. We compare it to the alpha level. It's larger than the alpha level. Okay? If it's bigger than the alpha level, F2R. We failed to reject the null. There is a lack of evidence that the true mean lifetime, the parameter, is greater than 30. Okay, so you have a decision to make, which is comparing the p-value to the alpha level, and then you have to interpret it. Make sure, you can write on the FRQ that you understand what you're saying. You're not just comparing the p-value to the alpha level. You never accept the null. Okay. So we'll get into this. This is your conclusion on the template. We're a little ahead of ourselves here. But the issue is you can make a mistake. Okay, because the parameter is what we're trying to identify, but we're rarely, we're rarely going to discover the true parameter. So there's a possibility you can make a mistake. And there's two types of mistake you can make, a type 1 error and a type 2 error. So this table is really helpful, okay? So there's a two-way table here. What happened? The null could be true or the null could be false. They're the columns. The rows are, you could have rejected the null or you could have failed to reject the null. So if we go here to the northeast, you rejected the null and the alternate was true. That's what you're supposed to do. We go to the southwest. You failed to reject the null when it was true. That's what you're supposed to do. These other corners are mistakes. What happened? The null was true and you rejected it. That's a type 1 error. The alternate was true and you failed to reject the false null. That's a type 2 error. So here's how you remember this. F2R. F, the number 2R, goes with the type 2 error. If you fail to reject the null, the only mistake you could possibly make is a type 2 error. But you literally build this two-way table and it walks you through it. So, I'll give you a minute to read this question. Now, this is an AP level question, ready? Because it says, here is your, describe the type 1 and type 2 error in the setting, and what's the consequences, okay? So the null is, the proportion of bruised potatoes is 8%. You can live with that, okay? The alternate is, it's greater than 8%. So it's greater than 8%, you don't want to use those potatoes. You're willing to accept 8% banged up tomatoes, or potatoes, sorry. So what happens? Type 1 error. The type 1 error is you reject the true null. So the type 1 error is the null is true, that the banged up potatoes are 8%, but you rejected that because you assumed that you found that more than 8% of the potatoes were marked. So what's the consequence? Well, you send away the truck when they were fine. Well, that's going to cost you money. What's the other possibility? Type 2 error. You failed to reject the false null. There really were more than 8% of the potatoes that were blemished, but you didn't recognize that. So what's the consequence? Well, you made potato chips with substandard potatoes, and the people might not be happy with your product. So there's consequences to each. So we talked about this. This lends itself to, well, how do you pick the alpha level if you're not given the alpha level to begin with? Like, how do you make a decision? And that goes in terms of you weighing what's more serious in context, a type 1 or type 2 error. So the probability of a type 1 error is the alpha level. Now, see if this makes sense. This should make sense to you. You draw the curve, okay? And at the 5% significance level, if it's a two-tailed test, we would have 2.5% in each tail. So what that means is you could land in that tail, either tail, 5% of the time by chance alone. So it's like as if the curve were a dartboard and you're throwing darts at the curve. And if you miss the curve, you get a takeover. You're going to keep throwing them until all your darts hit the curve. But if you have 2.5% in each tail marked up and you're throwing the dart, the total 5% of the time, even though you're aiming for the center, you're going to land in the tail by chance alone, and you're not going to get your takeover. So that's the alpha level. The probability of making a type 1 error is the alpha level. Okay? So if the alpha level were smaller, there's less of a chance of making type 1 error. But if there's less of a chance of making a type 1 error, the probability of making a type 2 error goes up. Okay? So what happened was the second bullet point, what is a p-value, and interpret it. So that was introduced to you in the alpha lesson, and we came back to it, like in that, in the problem for the potatoes. And a type 1 and type 2 error can give a consequence, okay? So, when you make a conclusion, you're comparing the p-value to the alpha level. If the p-value is smaller than the alpha level, you reject the null. If not, you fail to reject the null. Here's the table that was on the PowerPoint. The null could be true or could be false. Your decision. You could reject or you could F2R. If you F2R, the only possible error you can make is a type 2 error. Right? And the probability of making type 1 error is the alpha level. So we're going to pause the video. We're going to ask you to go to two problems, 23 and 27, and we'll come back to those. All right, so let's look at 23. The null is that the mean income in the neighborhood is 85,000. Okay, the alternate is it's more than 85,000. Okay, the type 1 error is rejecting the true null. So you reject the true null. The people make 85,000. You assume that your conclusion is they make more than that. So you open this restaurant in a location where there's not enough, people aren't making enough money to support it. The type 2 error is failing to reject a false null. Your conclusion is people do make 85,000. Okay, so you say, well, this neighborhood isn't affluent enough to support my restaurant, and you go somewhere else, when in reality, the neighborhood was affluent enough and you gave up a good location. Okay. 27. So we're talking about left-handers, okay? Now, the parameter is 10%. We're going to test that, and the alternate, it's a one-tail test that is greater than 10%. So you have this simulation here, and the simulation is based on 10% lefties. Okay, so they did 200 trials, okay? And they're each 50 students. So what happened? 8 times here, or 8 out of 50, 16%. How often did it happen? 24 times. Where are we getting this? The height of the dots above. 16% and everything to the right of that. So here's 10 dots. Here's 8 dots, 3 and 3. So that's 24 to 200 trials. Resulted in getting 16% or more left-handers out of 50, because that's what you got in your observation. So what is that? Well, it gives you a p-value of 12%, which is greater than 5%. So you fail to reject the null. There's a lack of evidence that the true proportion of left-handed students exceeds 10%. F2R, okay? So this document is in Google Classroom. So Kerry McCann, who graduated 2.5 years ago, drew this picture, type 1 and type 2 error, okay? And it's color coded. So you can see here's p hat. And what happens is, if you were to move p hat to the left, the type 2 error goes down, but the type 1 error goes up. So you're comparing this area of the curve. So here's the null in purple, and the alternate is in green. Well, your null hypothesis is centered about the purple distribution, and then here's what you get, p hat. So if p hat's really close over here, that's increasing the probability of making a type 1 error. As you pull this to the left, you pull it to the right, it increases the probability of making type 2 error. Okay? So what's going to happen is, that is all for the beta lesson.